All right, you all are in for a real treat because this presentation is so visual that it is too large to run in Google Slides. So we are going back to old school PowerPoint. Stig, take it away.
Oh man, and I'm clearly the person who didn't read the email about the standard template. So sorry about that, Robert. All right, hi everybody. I am from across the pond. I work in a company called Stack HPC. We started the business getting on for 9 years ago with this idea of creating an open source support for research computing infrastructure moving into the sort of cloud transition. So the idea was we'd make cloud for research institutions, universities, and the like in a way that supported their workloads and their requirements and didn't also suck in terms of performance. So we are also very proud to be contributing to the OpenStack projects and other aspects of the open source community. This is our contributions for Caracal. I even did a couple of those, but probably not very exciting ones. And we are supported by a wide range of clients who enable this work and enable us to make these contributions. So what I wanted to talk about really is several things that in our recent R&D efforts. And really, they boil down to this idea that open infrastructure is kind of the art of the possible. So one of my team, one of my former team members, he said that OpenStack is like choose your own adventure. And so how do we make the machines that we want to build without getting bewildered by the range, the sort of vast explosion of options that there are available to us when we produce these things. So the idea is that business like ours, we have the expertise to produce something which is a little bit easier to work with, and maybe for the users of the cloud services we provide, it's a little bit easier for them. They don't have to be sysadmins, they don't have to be Linux admins or Slurm admins or other things in order to get quickly into working on scientific research. So we try and produce systems that spring out of the box in a working solution and are easy to maintain for our users. The way that we do this then, there's three broad categories to that. We try to create a reconfigurable substrate of infrastructure as code with strong multi-tenancy and self-service. We try and make that as fast as possible in order to give it using sort of best practice from public domain knowledge. And then we build on top of that this user-friendly environment to enable scientists or other researchers to get quick access to the kind of project that they want to work on. The reasons for this, so just a little bit of context, is that the modern research computing is getting pulled in various different directions. So you've got your classic conventional Slurm people. They just want to have a batch queued environment and they want to SSH into it and run chemistry simulations or other things. But next to them, there may be data scientists who maybe come from a completely different faculty within the university, and they've felt kind of ignored for the last couple of decades because everyone's focused on high-performance computing infrastructure for Slurm and batch compute. So data science is increasingly becoming a very significant use case. And so people working in Python notebooks and that kind of thing, very important. But there's also people who just want to have a bigger machine than their own laptops. Maybe they're working in their office and they have this idea that that they're working on their laptops and then suddenly they outgrow the RAM of their laptop or the storage. But the environments that they're moving to in terms of research computing are completely alien. They have no relevance or no similarity to the laptop environment. So they want something in between, like a big beefy Linux desktop, a workstation that they can develop on and move into a research infrastructure environment. Next to that, we've got the burgeoning demands for machine learning. And so how do we provide software stacks that are evolving so fast that, yesterday's software stack is out of date? And so how do we enable users to bring in the sort of huge agility that they might need to get machine learning and stay on the cutting edge of this very fast-moving space? You may also have people in a research environment who are providing a citizen science portal. Maybe they're providing a web service to users. Maybe they want to be interacting with a wider community. And so they want to produce something like a web platform hosted on Kubernetes. And then finally, maybe you have people attached to the local hospital or working on medical informatics, or they have trusted research requirements that are not met, or for which a conventional computing infrastructure is not sufficient to meet those assurances that they require. So how do we do all of this? Well, we start by building this substrate where instead of buying and deploying services as independent silos, so we might have a separate machine for high performance computing, separate one for data science, a separate one for machine learning. We try to do this, and we try to build a single cloud substrate and build the other things on top of it as software-defined platforms. So of course, OpenStack comes to the rescue here. And what we do is we use the strong multi-tenancy, the infrastructure as code, and a set of standard APIs and some nice principles around CI and automation in order to produce the result of a shared reconfigurable infrastructure. So the way that works, kind of not quite as nice as James's diagrams, but maybe we get a whole bunch of bare metal nodes, and day one we go for the hero number, we deploy Slurm, we get our machine into the top 500, and then we sort of right-size the Slurm cluster, and we start to build other things into this environment. So we're using that reconfigurable infrastructure to good effect here, and we're using isolation so that we can put a data science environment next to our Slurm cluster, size it according to what we need on the day, and then maybe we can also go from there to add other things. So we can start to add in virtualization using the same resources that we would otherwise be using for Slurm or data science. So we put in a service project, we boot a bunch of nodes as hypervisors. They come back into service, they sign on as Nova resources for exploitation. We can then put a bare metal trusted research environment on dedicated hardware using VLAN isolation and run our sensitive data workloads on a fenced off partition like this. Maybe then we have users in the system who are only allowed access to the virtualized compute resource. They can do the machine learning. We can run the virtual desktop infrastructure. And maybe we can also run an extra partition from our Slurm cluster for like the kind of quick turnaround, real-time compute, or open on-demand kind of VDI partitions, these kinds of things. We have flexibility to do as we wish. So this is really the vision, I guess, of this shared reconfigurable infrastructure and what it can provide for us. The way we do this is this little project called KOB. It was started by a colleague of mine back in 2017, builds on Collar Ansible and adds all these other components in order to take bare metal infrastructure and get it to the point where we can deploy Collar Ansible containerized OpenStack services. Everything that is possible to define on the infrastructure is kept in one single Git repo, so we have a nice sort of transactional serialization of all the changes backed up with things like CI and automation. Moving on then, so all this is very nice, but if it has overheads that make it prohibitive, then that's no good. So we want to be able to use this infrastructure and configure it using best practice. And of course, the best way to answer this is in the context of robot Shakespeare. To virtualize or not to virtualize, that is the question. And so really, there's a big sort of choice here. It doesn't have to be either or, as we've seen, but we can use bare metal, as James was talking about, in order to get ourselves close as possible to the hardware. And so then there's zero overhead from the cloud infrastructure, but at the same time, we get pretty much all of the interfaces and all of the flexibility that a cloud can provide for us. If that's that solves the problem for a lot of our use cases, but big machines these days are big. They're big fat things. You know, there may be a terabyte of RAM in them. There may be 256 or more CPU cores. Running a notebook on this, which is sequential, is kind of wasting it. So we need to be able to use some of our machines in a more partitioned, more kind of fine-grained manner. And this is where the virtual machines come in. And so we can use virtual machines to provide a more flexible interface, much quicker to work with, much nicer to work with, and really the performance overhead when you push it hard is only a very small percentage. So the approach that we take is, when we are making machines that are virtualized but still aiming to be fast, is that we kind of pizza slice the hardware. So we take a thin slice for the operating system, the data movement activities of Ceph, other housekeeping activities, and then we take the rest of the machine and slice it into even chunks and pin those cores and pin that RAM and associate a guaranteed fraction of our hypervisor resources for each of the virtual machines. So there's an interesting question here, which is a typical CPU, a typical server system today has a pair of CPUs, a pair of sockets. There's almost like a light year of distance between the two of them compared to going between the CPU cores within one of the individual sockets. So when we want to make a machine which is sliced up like a pizza, do we make our machine so that all of the CPU cores we're giving to a virtual machine are within just a couple of NUMA nodes like this? So we split a machine into 4, and we put only 2 NUMA regions into each of our virtual machines. This gives us great locality between the CPU cores. So they are right next to each other. They can speak very fast to each other. This gives us really good inter-process communication. We could strike a middle ground and say, we break our 4 machines into, each one has like a quarter of each of the CPU sockets. And so it lives within one socket in our system. This gives us somewhere between, so we get the memory bandwidth of an entire CPU socket and reasonable locality within that socket as well. We don't have to go off chip to make any communication. The other way to do it is that we go wide. And so now we have CPU cores on every memory controller within our system, and we build it up this way. So now we've got huge fat memory bandwidth, but actually kind of loosely coupled CPU cores. So they're not really that good at interlocking and communicating with each other. All of these things we can do in an OpenStack flavor, or just set these properties, and it just comes out. So anyone can do this. The way that we see it then, so in terms of memory bandwidth performance, when we divide into pairs of NUMA regions, we see this nice staircase of each of these virtual machines as we go from, there we go. So 1 VM, 2 VMs, 3 VMs, 4 VMs. We blast the memory, and we get this very nice kind of isolation. So they can't disturb each other. Each of them gets a quarter of the memory bandwidth of the whole hypervisor. When we go to virtual machines per socket, the first two, so 1 VM and 2 VMs, we see a big uplift, and so as we get the whole socket's performance. And then the nice thing is that when we get into this contentious environment where they're competing for memory, it actually degrades very fairly, so they get nice arbitration. On the other side, when we go wide, we get huge memory bandwidth for one virtual machine. And then as the more machines become active on the system, on our CPU, it degrades fairly so that they get as much as they can, and they get a decent slice each. Slight problem is you can't actually do this in OpenStack today. So there isn't a way to say in OpenStack, in Nova, I would like to have just the CPUs on one socket, please. But you don't get this. You have to be able to say, I'd like 4 NUMA regions, and OpenStack will say, OK, well, I'll just pick 4 randomly from within the machine. So this is something that we, within Stack HPC, I would very much like to work on and develop this capability of socket awareness as well as NUMA awareness. What we don't get then is, in a typical physical system, we get this idea of NUMA distance between any particular cores. In a virtual machine, we don't have that. We just get this flat landscape. It kind of hides all of the knowledge there. This is the only photo I've got in this presentation of the Dawn system, which was in the keynote this morning. It's 1,024 Intel Ponte Vecchios. It is a hair's breadth from being the fastest system in UK academia today. There were a couple of nodes offline, and if they hadn't been offline, it would have been number 1. So unfortunate. But in terms of the networking, and I should probably speed up a bit here, There's some nice things that we can do for hardware offloaded networking for these kind of AI clouds. We need tight coupling, we need high bandwidth, we need low latency. SR-IOV is the sort of the established way of doing this. Ethernet-wise, that's pretty close to what you get on the wire in terms of rocky message latencies. It gives you a very nice, very simple, minimalist kind of approach to high-speed networking within the VM. Taking it up a step, there's this thing ASAP squared, in which we offload a lot of the rich capabilities that OpenStack provides in Neutron, and we can actually program those into the pipelines, the packet pipelines on the network cards. And this gives us higher latency, but still way lower than TCP/IP for our messaging, and can give us message bandwidths close to saturating the physical capabilities of our machine. But at the same time, we get features like firewall, so we get security groups, we get the use of a redundant pair of physical ports, we get live migration, we get the whole shooting match. It's a pretty good combination. So the way that it works, we have a network card here, we get 2 physical ports out the back, we get a bit of magic in the middle there, and then we get virtual functions which plug into the VMs down here. They look like they've got a physical device in them. They can talk high-performance computing protocols to it. It kind of works, and the bit in the middle does all the glue between the outside and the inside. The way that we use this then, so if we have a set of tools for deploying Slurm clusters into virtual machines, this is called our ping matrix. So whenever we build one, we run a bunch of self-tests. This is 16 nodes spread across 4 hypervisors. This kind of diagonal blocking is the nodes that are messaging each other from within one hypervisor, and then the darker blue is the stuff between hypervisors going across the fabric. And so we get decent latency, sort of 3 and a bit between 2 nodes, and within a node about 1 and a bit. Once we've got this substrate, and it's fast and it's flexible, it's reconfigurable, we need to make it usable. And so we've put a lot of work with some colleagues at the Jasmine Environmental Science Cloud in the UK into this project called Azimuth. And really this is an alternative to Horizon, and it's an alternative to providing infrastructure as service for scientific users. And so the purpose of this is that it provides users who have, they are the end user of the system. They want to log in and deploy compute platforms like Slurm or Kubernetes or Jupyter Hub, and they just want to get on with it. They don't care how it does it, but they want to be able to self-service those kinds of environments into their cloud, into their projects. As an example then, so the people who just want the bigger laptop, they'd log into the portal, they'd choose their project, and then they'd be presented with, yeah, okay, make something. And you choose from a catalog, and the catalog is curated, it's managed by the admins of the system. And so they could choose from these list of options, and they'd say, okay, I want the workstation. They said, well, how big, how much data, how much storage does it need? And then they'd be presented with 2 things here. So firstly, how does this impact my quota on the system? And then how long do I want this thing to live for? Which is a little bit of a weird one to consider until you realize that as soon as you make a machine with GPU nodes in it, if you don't give them a lifespan, someone will come along on day 1 and build a GPU VM and own that, because they know that as soon as they give it up, they'll never get it back again. So we have this anti-sort of cyber squatting arrangement where for fair share, yep, you can have it, and you can have it for 5 days. And then make the most of it, be productive, and then it's somebody else's turn. So the machine starts to build, and the next thing is, once it's ready, we have this reverse application proxy, which exposes named services from this environment. This machine, this workstation doesn't have a public IP, doesn't have any externally reachable way to get to it other than through this portal, through Azimuth. So when we go through and we click on the guacamole, we have a web interface for it, which is behind our portal. So it's authenticated using our OpenStack authentication. And there's no other way to get into it. So inherently, it's secure in a way that floating IPs typically aren't. So then we go through, you get to the desktop. Being a web application, or being sort of deployed with automation, we also get things like monitoring infrastructure so that if we have users who want to be calling the help desk and trying to work out what's going on, we keep track of everything that is useful or is helpful to them to enable them to understand why their machine is slow or why it's run out of RAM or whatever else. Building on that then, so a single node virtual desktop is nice, but we need to look at these sort of multi-node compute platforms. Kubernetes is a good example, and so a lot of the platforms within this catalog are actually building on top of a Kubernetes platform running within the project. So we'd choose a version, and we'd choose our nodes, and then we'd provision the thing and add some extra little pieces. Once again, we get a lifetime for our cluster, and we understand how much is going to impact our quota. And the thing goes off and builds. And then one of the useful pieces here is because it is using a platform as code kind of approach, the admins and the people who are providing this service can integrate in the best pieces of operators and add-ons to this system to make sure that it runs really well on this environment. So we don't have a bunch of people setting up their own Kubernetes and going off and running KubeSpray, and it kind of works, but it's not brilliant. And then 6 months later, it's out of date and it's looking a little bit smelly. We don't have that kind of situation because this is essentially a managed configuration for our Kubernetes deployments, and we're not expecting the users to be experts in this in order to use it. So we get the nodes, they come up, and once again, we can expose the features of our Kubernetes cluster, like a kube config or a web interface. We get the monitoring for the kube platform, and also the logging and the other details coming out of it as well. Using it, so Dask is a extension to sort of a Jupyter Hub environment to provide this sort of distributed task flow for data science. A nice example of an application that runs inside our Kubernetes cluster. So maybe we're running a data science class for our users. Maybe there's a workshop. Maybe it's 100 people, like here at the conference. And we need to deploy a Kubernetes cluster, and then we put this Dask platform into that cluster, and it's all very easy to click through. The users are passed through, so it's single sign-on. So as soon as I create a notebook, I don't have to log in again. It's all passed through, so it's a single authenticated browser session. But the nice thing is, if I go through these bits, I can provide access to my Dask platform to users who aren't users of OpenStack. So maybe in my job, I'm running a seminar, I'm running a GPU machine learning workshop or something. I've got 20 students. They don't have OpenStack creds. I can go through and create a dedicated access just to the Dask Hub services, so not to the monitoring, not to the other things. And I can provide users with a way to sign in using their institutional identity. So they don't have to be OpenStack users in order to use the services that we're providing for them on the open. So then the user comes through, and they get their institutional identity. Maybe they've logged in with AD or something like that, and they get access to a notebook themselves. Final one, I think I'm probably low on time here, but we can deploy a Slurm cluster within our compute project. So this is not like a production Slurm service. This is a service a cluster which is deployed for the exclusive use of a research team. So it's kind of like a little private Slurm cluster just for them. The Slurm cluster is defined using Terraform and Ansible, kept under version control alongside everything else in the catalog. And the users then, they get access to it. And because, as was hinted, Slurm users tend to just like to be able to SSH in and do the console stuff. So we can access it through a floating IP. This appliance creates one by standard. But it also provides open on demand. So we get this kind of more user-friendly easier to get started with kind of environment where we can have desktops or Jupyter Hub environments through OOD as well. Because we added things like the monitoring of jobs. So any jobs that run inside our Slurm cluster, we get details and we get we can click through to a kind of a time-boxed telemetry of what was happening while their job was running through a sort of a sidecar Prometheus service running within it. How to get involved? So everything here is open source, and everything is under readily available. You guys can pull down these things and get started. There's a lovely developer mode of Azimuth where you can just run it in a single node. It kind of springs out the box. Please do go ahead and try it. And if you get stuck, we exist to help with expertise and consultancy on design, deployment, training, and support. The other way to get started is to come along tomorrow to the Scientific SIG. We have a forum session tomorrow afternoon at, it looks like 1:30. So that's just next door. And I hope to see some of you there. It'd be great to see you. So thank you very much. Apologies if that's quick. I had a bit too much coffee.
I'm glad to hear you have enough coffee. Any questions? Hang on.
James.
Y'all are catching on, right? You got to wait for me.
Comment that it's really cool to see that you're using the Mellanox ASAP Square technology. I haven't seen anybody using that yet in production. Have you noticed any discernible difference? I saw you had some metrics on there between SR-IOV and ASAP Square. Like, what is the performance penalty?
It's about 2 microseconds latency. So, and it's interesting. So we've studied it in different ways. For everyone else, the ASAP Squared is this capability to offload the Open vSwitch flow rules onto the network card itself so that it's programmed into the packet pipeline on the silicon. And it's very cool technology. We use it, so it's principally to get remote DMA capabilities into virtual machines. And we have, I mean, yeah, it gives you really good performance on a sort of a configuration that's just so on a pair of 100 gig Ethernet NICs, we get 180 or 190 gigabits a second out of the pair of NICs. So it has very high bandwidth. The other implication of it, though, is that you do need to have things like flow control, so lossless Ethernet coming out of the box. And so it's got a lot of complexity to get it set up. And it's a little bit brittle, I think. So having the good test environment where we can qualify the next kernel, the next Open Fabrics release, those other pieces is very important.
Another question? We might have time for 2 more.
So just to clarify, the Azimuth tooling, does that rely on just a regular OpenStack hypervisor plane, or is this something that actually digs down into, because you mentioned ironic earlier, or let's say a low-level hardware deployment layer? Are you necessarily needing that, or can you just deal with that at the regular, let's say, VM level?
So it builds on a regular OpenStack. It's actually deployed into like a service project on the cloud, and it's run from a smallish Kubernetes control plane of its own. It does need a few things that Kubernetes needs to work. So it needs like load balancers. So you need Octavia running on the system. You need so the etc.d that Kubernetes uses tends to need some kind of like local storage or low latency Ceph or something like that. So it can be a little bit sensitive as well. So it doesn't run on any arbitrary OpenStack, but it will run on a general OpenStack that has those capabilities.
So have you run against any scaling limits on Nova or Neutron or those kind of things? Or are you, you work around them, multiple clusters, those kind of things?
I guess the biggest virtualized clouds that we run against typically, I mean, the modal point is probably around there's a few hundred hypervisors or so. The majority of the clouds that we work with in research computing are slightly below that, sort of plus or minus 100. And so I think that the scaling limits that we see there are, it's not a problem. Certainly, we see advantages to the way that OVN is scaling versus Open vSwitch and the ML2 driver. In terms of bare metal, the biggest machines are multiple thousands. So ironic scales, because it's far simpler what a node is doing, it scales much better.
Stig, thank you very much.